Okay, hi. Today we're going to start about functions, and most of the session is conceptual. So we're going to add graphs and equations. But first, we are going to look about what we mean by functions. Or y is equal to f of x. What do we mean by that? Before we start this, if I throw these numbers 1, 2, 3, 4, and you know this is a relation between the two ordered pairs, the x and y, the value of x, the value of y, the value. So we call this as relation. So a function is a relationship between x and y, but it has a distinct meaning. Let me define it. A function is a special kind of relationship. Special kind of relation between x and y, in which for one or more values of x, there is exactly one value of y. The key note to take is there is exactly one value of y. That's what we are going to zero in. So let me start with our example of relation, the ones that I have looked. Look at the ordered pairs. When x is 1, y is 2, when x is 2, y is 3, 3, 4, 4, 5. It satisfies our definition of functions because for one value of x, there is exactly one value of y. So this is a function. Another example of a function would be 1 and 2. Negative 1 and 2. 2 and 3. Negative 2 and 3. We have now two different values of x, but we have one value of y. Two different values of x, one value of y. Again, it satisfies our definition of a function, so this is also a function. I can go ahead, 1 and 2. 2 and 2. 3 and 2. In fact, I could do. You have probably infinite values of x. Negative 1, 1, 2, 3, 4, up to even infinity. But there is what? Only one value of y. Again, this satisfies our definition of a function. Okay. Now, then, if all of these are functions, what is not a function? Look at this example. Now, this is not a function. Why? Because we have one value, the same value of x, giving us what? Two different values of y. The same value of x, giving me two different values of y. When that happens, this is not a function. Not a function. In fact, I can do this. we have the same value of x, but it is giving us what? Infinite values of y. This is another instance of this relationship being not a function. In short, this also might be helpful. So you know what a domain and a range is. And let's say this is our domain and this is our range. You know domain is always x and range is y. You can have as many values of x as input, x2, x3, x4, up to infinity. But once you get through the process, the only outcome you are expecting is just one y. Okay? That is basically what we mean by a function. Okay? Now let's look at the concepts of symmetry. And we'll use the Cartesian coordinate system to talk about this. Symmetry. Symmetry, reflection, these are concepts. So let me draw the Cartesian coordinate system. And in the Cartesian coordinate system, you know that they are divided into 4 equal parts. This one is quadrant 1, this one is quadrant 2, this one is quadrant 3, and this one is quadrant 4. Let me draw a graph in quadrant 1. And as you know, in quadrant 1, all values of x and y are positive. So I will denote it as xy. And let me draw a reflection of that graph in quadrant 2. And in quadrant 2, what is changing is the signs of x. So we have negative x and y. This is a reflection of each other. If you stand by the y-axis, you can see clearly negative xy is a reflection of xy. So, if we replace x by negative x and end up with an equivalent. It's an equivalence. By equivalence means it's the same graph with an equivalence. Then we say the graph is symmetric with respect to the y-axis. If you stand under the y-axis, you see xy, negative xy is a reflection of xy. Now let's change this. Instead of drawing a reflection in quadrant 2, let's draw the same reflection in quadrant 4. And let's label those relations. In this instance, the value of x stays positive, but the value of y stays negative. And you can see the reflection Now, not standing at the y-axis, but if you stand across the x-axis. So that's how you see the reflection of xy into x and negative y. So if we replace y by negative y and end up with an equivalent, then we say the graph is symmetric with respect to what? To the x-axis. Now let me change the reflection to a different quadrant, and this time to the third quadrant. If I do it in the third quadrant, look what happens now. In the third quadrant, all values of x and y are negative. So we have negative x and negative y. Where do you see the reflection of xy from? From the origin. If you start by the origin, you know negative x, negative y is a reflection of xy. Therefore, if we replace y by negative y and x by negative x, meaning what, replacing both positive values into the negative values, and end up with an equivalent, then we say the graph is symmetric with respect to what? To the origin. So we have three instances of symmetry. Symmetry with respect to the y-axis, symmetry with respect to the x-axis, and symmetry with respect to the origin. If an equation does not satisfy the three, one of the three, then there is no symmetry in that graph. Okay. So let me use equation as an example. Suppose you have x is equal to y squared minus 1, and you are asked to test for a symmetry, meaning what? You are going to find out whether this is symmetric with respect to the y-axis, the x-axis, or the origin. So let's say symmetry with respect to the y-axis, and let's try to solve this. Let's question it whether it is symmetric with respect to the y-axis. In order to do that, I have to change x into negative x, right? So my x becomes negative x is equal to y squared minus 1. Then change negative x into x because we are actually trying to find whether there is an equivalence. So if I multiply both sides by negative, then I end up with negative y squared plus 1. But x is equal to y squared minus 1 is not the same as x is equal to negative y squared plus 1. Therefore, symmetry with respect to the y-axis? No. It's not symmetric. Let's try to test whether it is symmetric with respect to the x-axis. Then I have to change what? Y into negative y. So x is equal to y squared minus 1. Then I'm replacing y by negative y. So I have negative y squared minus 1. And as you know, negative y squared is the same as saying y squared. So because negative y times negative y is y squared minus 1. We got the same equation of x is equal to y squared minus 1. Therefore, what we can conclude is it is symmetric with respect to the x-axis. Yes, it is symmetric. Sorry for the distraction. Now, let's try to solve whether it is symmetric with respect to the origin. This requires me what? To change x into negative x and y into negative y. So negative x is equal to negative y squared minus 1. So negative x is the same as saying y squared minus 1. Automatically, you know this is not symmetric with respect to the origin because you're going to end up with non-equivalent equation. So you say no. Okay. So when you do the assignment, you have to test for all the three aspects of symmetry. Let me do another one. Y is equal to x cubed. And let's try to find out whether this equation is symmetric with respect to the y-axis. So, meaning what? With respect to the y-axis, you have to change x into negative x. So this is y is equal to negative x cubed. Because it is negative x cubed, the negative does not go away. So you end up with what? Negative x cubed. But y is equal to x cubed is not equivalent to y is equal to negative x cubed. So you would say not symmetric with respect to the y-axis. Now, how about with the x-axis? With the x-axis, you have to change y into negative y. So, negative y is equal to x cubed, right? And if you get rid of the negative number, y is equal to negative x cubed. And this tells you y is equal to negative x cubed is not equivalent to y is equal to x cubed. So, therefore, it is not symmetric with respect to the x-axis. How about the origin? For the origin, you have to change both x and y. So what you are saying is negative y is equal to negative x cubed. Right? So negative y is equal to negative x cubed, but if you divide or multiply by negative 1, you end up with what? Y is equal to x cubed. So these are two equivalent equations, the same equation actually. It is what? Symmetric with respect to the origin. So it's not symmetric with respect to the y-axis, not symmetric with respect to the x-axis, but it's symmetric with respect to the origin. In fact, if you can go ahead, and this could be a good exercise and practice, and draw the graph of y is equal to x cubed, you end up with a graph that looks like this. In quadrant 1 and quadrant 3, that tells us that it is symmetric with respect to the origin. Y is equal to x cubed. Now, even and odd functions. And this is not that difficult. So it's quite interesting. If f of x is equal to f of negative x, meaning what? If I replace x by negative x, it does not change its outcome. Then we have then our function is even. If we replace x by negative x and end up with the same equation, with the same function, then we call it even function. If f of x is equal to negative f of x, okay, note the difference. Then we have, then our function is odd. If neither, so it is neither even nor odd. Okay, so we have to look for these two conditions. Okay. So let me just give you examples of this. F of x is equal to x cubed. Let's say f of x. Then if I put f of negative x is equal to negative x cubed. Right? So f of negative x is equal to negative x cubed. Therefore, if I replace, if f of x is equal to, but f of x is not equal to f of negative x, because we ended up with what? X cubed is equal to negative x. Therefore, this is not an even function. Is it an odd function? By odd function, what do we mean? F of x has to equal to negative f of x, right? Okay. So, if f of x is equal to x cubed, negative f of x is equal to negative x cubed. And negative f of x is equal to negative x cubed. It is the same. F of x is cubed. If I change f of x into negative of x, so negative of f, if I multiply both sides by negative 1, I end up with what? F of x is equal to x cubed. I end up with the same equation. So we say what? This is an odd function. In fact, change this so that I don't want to confuse you. Change this to y is equal to x cubed. So you can do negative y is equal to negative x cubed, or y is equal to, in fact, let me change all of them. It means the same thing, but some people get that. So negative y is equal to negative x cubed, so y is equal to x cubed. So you end up with the same equation if you apply f of x is equal to negative f of x, and that's what makes it an odd function. Let me do another one. This. F of x is equal to x cubed minus 6x. Now, let's find f of negative x. If f of negative x, then we have what? Negative x cubed minus 6 times negative x. Then f of negative x, this would be negative x cubed plus 6x. Now, for a function to be an even function, f of x has to equal to f of negative x. But x cubed minus 6x is not minus x cubed plus 6x. Therefore, f of x, since f of x is not equal to f of negative x, it is not an even function. How about if it is an odd function? An odd function means what? If f of x is equal to negative f of x. So f of x is equal to x cubed minus 6x. Then negative f of x, negative of x cubed minus 6x, negative f of x is equal to negative x cubed plus 6x. But then, if f of negative x is negative x cubed minus 6 times negative 6x, so f of negative x is equal to negative x cubed plus 6x. Now look at what negative f of x gave me. Negative f of x gave me negative x cubed plus 6x. And f of negative x also gave me negative x cubed plus 6x. Because f of negative x is equal to negative f of x, according to our definition, so this is an odd function. You can see this. Maybe let me do another one. Probably I'm going to 2 examples. Let's do f of x is equal to x squared plus 6. So if this happens, f of negative x is equal to negative x squared plus 6, but negative x squared is what? X squared plus 6. Therefore, f of x is equal to f of negative x. Therefore, this function is even. Suppose let me do f of x is equal to 7x cubed plus 6. So let me do f of, first let me do negative f of x. Oh, let me do f of negative x. F of negative x is equal to 7 negative x cubed plus 6. So you end up with negative 7x cubed plus 6. And as you can see, this is not an even function because f of x is not equal to f of negative x. And let me do negative f of x. If I do negative f of x, so this would be negative of 7x cubed plus 6. Then you end up with negative 7x cubed minus 6. Oops. Please disregard this. I chose a different number. It's not going to change anything. So let me redo this again. Just do the x. My apologies. So let's find whether this one is even or odd. So f of negative x is equal to 7 negative x cubed plus negative x. So you end up with negative 7x cubed minus x. But since f of x is not equal to f of negative x, so this would be not even. But it is an odd function because negative f of x would give us negative 7x cubed minus x, because we can distribute. So f of negative x and negative f of x are the same, so therefore this is an odd function. Sorry for the mishap. Okay. Now let me do one more example and then we might end the session. Suppose now f of x is equal to x squared plus 2x plus 1. And let's see whether this one is even or odd. Plug x, change x into negative x. F of negative x would give us negative x squared plus 2 times negative x plus 1. And this is the same negative x squared is x squared minus 2x plus 1. Since f of x, x squared plus 2x plus 1, is not the same as f of negative x, x squared minus 2x plus 1, not even. Now, we know this is f of negative x. What would be negative f of x? If it is negative f of x, then you have negative x squared plus 2x plus 1. The entire expression would be negative, so you end up with negative x squared minus 2x minus 1, right? And because f of negative x is not the same as negative f of x, and it's also not odd. When you see this, then you say neither. So these are examples of even and odd functions, and once you get the assignments, I think it would be much clearer.